Okay, in the last video I talked about in the textbook there being a table of, actually Maclaurin series is what they are, and I think I said section 10.7. It's actually 10.8 in this new edition of the textbook. 10.7 deals with Taylor polynomials, which are just the truncated versions, if you will, of these Taylor series. And it's helpful to maybe look through that section as well to get a feel for how those graphically converge towards the actual function they represent. But here is the Maclaurin series for e to the x. We derived that one in the first video. Sine x, we derived that one in the second video. Here's cosine of x. Here's 1 divided by 1 minus x, which we had when we originally talked about power series. And you see where it converges to the function for all values of x. Now this one's a little limited, obviously, because it only converges for values of x less than 1 in absolute value. That means between -1 and 1. And then on the next page we have some more examples. Okay. We actually derived the inverse tangent one by term integration of a power series that we had for 1 divided by 1 plus x squared. Okay. So these are some of them, but again, in general, creating Maclaurin series is maybe a little challenging. Taylor series, especially if you're centered about somewhere other than 0, with those Taylor series, that gets even more challenging. I want to take a look at a couple shortcuts to finding Taylor series, and in that, or Maclaurin series actually, but in that we're going to use these Maclaurin series that we have from this table. So let's take a look at that. So suppose I want to find the Maclaurin series for this function. Well, we've already, in the first video for this lecture, we already found the Taylor series for e to the x. Just rewrite it here to remind you of it. All right. And listing out some of the first few terms. When n is 0, we get 1. When n is 1, we get x. Then we get x squared over 2 factorial. X cubed over 3 factorial, and so on. Right, so there's our power series representation. So all we have to do then, if I want to find a power series representation for x cubed times e to the x, is to think about multiplying what? Sort of like the distributive property, multiply each term by what? X cubed. X cubed, right? What would it be? X cubed times 1 is x cubed. X cubed times x is x to the 4th. X to the 5th over 2 factorial. X to the 6th over 3 factorial. X to the 7th over 4 factorial. To the plus there, sorry. It's more like a multiplying sign. Okay. There it is. And so we can write this in terms of, so we're just taking basically all this stuff here, right, and then just distributing x cubed through it. And we can write this a little more compactly then as what? Summation n equals 0 to infinity. Just multiply this by x cubed. What's x cubed times x to the n? X cubed times x to the n is x to the n plus 3 power. And I'll have you check and make sure when n equals 0, notice you get x cubed. When n equals 1, you get x to the 4th. When n equals 2, you get x to the 5th over 2 factorial. When n equals 3, you get x to the 6th over, and so on. Right? So there is the Maclaurin series for x cubed times e to the x. Okay? So instead of going through it all the way, we can use what we've already derived. Since we've already derived the Maclaurin series for e to the x, we can do that. Okay. Now a little more challenging would be one like this, and I want to show you how to do this. We're going to write out the terms of the Maclaurin series up to degree 4 for the function e to the x times cosine of x. Okay, so what we're going to do is we're going to take a look at the power series representation for e to the x was what? We just did that. So there's e to the x power series representation. And then we derived in the last video, well, we didn't derive, we just gave, but essentially same as deriving for the sine of x function. Here's the Maclaurin series for cosine of x. Okay. And I'm going to write out again the first few terms here. Now, I don't have to do any terms that are what? Degree 5 or more. We're stopping at degree 4. So I'm just going to go up to degree 4 here. Okay, so there's the e to the x one. And then the cosine of x1, right, when n is 0, I get, oh, this should be negative 1 to the n, sorry. Negative 1 to the n. I've done that twice now. Negative 1 to the n, right, sign changer. So when n is 0, I get 1. X to the 0 is 1. 2 times 0 is 0 factorial is 1. I just get 1. When n is 1, I get negative 1 to the n is negative x squared over 2 factorial. So I get negative x squared over 2 factorial. And then what's going to happen? Positive, what, x to the 4th over 4 factorial. Remember, we're only getting the positive powers. And then so on. And so I'm going to, stop there because all I need is degree 4 or less. Okay, now what do? We've got two infinite polynomials. If I was really trying to find the entire Maclaurin series, I'd have to do an infinite number of multiplications. I don't have to do that because I'm only going up to degree 4. So how do I do this, right? This 1 gets multiplied by every term in this Maclaurin series over here for cosine of x. This x gets multiplied by every term here. This x squared over 2 factorial gets multiplied by every term here. This x cubed over 3, and so on. But I'm only going to pull out the ones that are degree 4 or less. So first of all, 1 times each of these gives me each of these. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Then I multiply x times each of these. X times 1 is x. X times negative x squared over 2 factorial is negative x cubed over 2 factorial. X times x to the 4th is x to the 5th. So if I'm doing the entire series, Maclaurin series for e to the x cosine of x, I would want to include that. But here we're saying only up to degree 4. So we're going to stop. We're not going to include that product because it's going to be degree 5. It's going to be more than degree 4. Go to x squared over 2 factorial times 1. Times this would have x squared times x squared is x to the 4th. And it should be negative here, sorry, negative. It's negative. Over what? 2 factorial times 2 factorial. What's 2 times 2? That's just 4. Right. 2 factorial is 2. 2 times 2 is 4. And then x squared times this, well, x squared times x to the 4th is x to the 6th. That's too big. So we're not going to include that. Go to this one, I've got 1 times x cubed. So that's back to positive. X cubed over 3 factorial. And then x cubed times x squared, that's x to the 3 plus 2, x to the 5th, too big. Don't include. And then what? Plus x to the 4th over 4 factorial times 1, x to the 4th times x squared, again, too big, x to the 6th. So we're done. So this is it. Now I'll put a dot here, because these are degree 5 or higher. And so there's an infinite number of those, right? But now we just simplify this, and you'll notice here that some things will simplify down. Here I got negative x squared over 2 factorial, positive x squared over 2 factorial. Can I just, that becomes 0, doesn't it? And I have, what else? Well, let's just see what I've got. The rest is I'll just simplify this out. So I've got a 1. I'll just cancel as I go, so to speak. That's what I probably should have done. X terms. Let's go to X. So that's the only constant term was 1. X terms. I got an X here. Any other X terms? No, just that one X. So I'm just crossing them off the list, so I keep accounting. So X squared, as I said, these cancel out, and so there's no X squared terms. No X squared terms. X cubed, I got this and this, and so this is negative 1/2, and this is 3 factorials. 3 times 2 is 6. What's negative 1/2 plus 1/6? Negative 1/2 plus 1/6. That's negative 3/6 plus 1/6. Negative 3/6 plus 1/6 is negative 2/6 is negative 1/3. That's going to be negative 1/3 x cubed. To do a little math in my head, that takes care of my x cubed terms. And then the x to the 4th terms, let's see what I got here. Let me do the coefficients here down below. I got 1 over 4 factorial, that's 1/24. And then I have minus 1/4. And then I have plus another 1 over 4 factorial, 1/24. Now to get a common denominator here over 24, what do I need to multiply top and bottom here? 6, right? So 1/4 is 6/24. And this becomes 1 minus 6 is negative 5, plus 1 is negative 4/24. 4 divides top and bottom, giving me negative 1/6. So that tells me I've got negative 1/6 x to the 4th, and then dot dot dot, right? These are going to be degree 5 or higher terms. So here's your Maclaurin series up to degree 4 terms. Okay, so again, very difficult to find the entire power series representation of e to the x times cosine of x, but you can get out the first, several degree terms that you want to. And this right here, again, if you graph this function with just these 4 terms, right, just this part, and compare it to the graph of e to the x cosine of x, it does a pretty good job, again, of approximating the function near x equals 0. And function approximation is where it's all at, so to speak. And I want to finish by just pulling this full circle. I want to take a look at, first of all, a Maclaurin series for the function f of x equals sine of x squared. Okay, so if you remember, we had the Maclaurin series for sine of x, n equals 0 to infinity. It was negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is the Maclaurin series for sine of x. And so for sine of x squared, what's it going to be? Let's list this out. This is when n is 0, I get 1. I get x to the first power over 0 plus 1 factorial is 1. I get just x. Right? When n is 1, I get negative x to the 2 plus 1 is x cubed over 3 factorial. And then what? Plus what? X to the 5th over 5 factorial. And then so on. So we see that pattern. We derive that. So that's what we have. So what is sine of x squared then? All I'm going to do in this is just do what? Replace x with what? Replace x with x squared. Replace x with x squared. So x replaced it with x squared gives me x squared. X cubed replaced with x. So be careful now. If I replace x with that, I've got x squared inside the cubing function. So what do I do with the exponents here? Multiply, right? X to the 6th. So that's going to be minus x to the 6th over 3 factorial, right? So I got the x to the 6th. And then what? X squared to the 5th is x to the 10th. And then what? x squared to the 7th is multiply x to the 14th. Okay. Which is due in summation notation. Think about replacing x with x squared here. Right? X squared now to the 2n plus 1 power. What do? I multiply the powers. I get x 2 times 2n plus 1 is 4n plus 2. Should distribute that through. So there it is. It's x to the, so it's negative 1 to the n, x to the 4n plus 2 all over 2n plus 1 factorial. And if you let n equal 0 in this formula, you get x squared. When n is 1, you get x to the 6th over 3 factorial. When n is 2, I get x to the 10th over 5 factorial. When n is 3, I get that term. Okay. So there is the Maclaurin series for sine of x squared. Now, here's where we bring this all the way back to the beginning of the semester. We've been dealing with a lot with these infinite series. How in the world does this relate at all, if at all, to integration, the first part? Okay? Well, here's where it comes to us. If I need to find this antiderivative, suppose I even want to find a definite integral for this, I certainly can use numerical methods like trapezoid rule or Simpson's rule that we showed to find a definite integral for this. But if I want to find the antiderivative of this, how can I do that? There is no way to find the antiderivative using any of the techniques that we developed. You try and use let u be x squared, you get sine of u, but you've got du is what? 2x dx. Where's your 2x dx? You can't deal with that. There's no x outside. If there was an x times sine of x squared, yeah, simple substitution. Okay? It's not going to go through all the trig. It certainly involves a trig function, but none of the trig integral techniques, trig substitution, none of those techniques, partial fraction decomposition, integration by parts, none of these are going to work. In fact, the antiderivative for this function cannot be expressed as a finite combination of our normal algebraic and transcendental functions. But it can be expressed as a power series. Right? And how do we do that? Well, I've just found a power series for this. So the integral of sine of x squared dx is equal to the integral of this power series, right? And I'm going to do it term by term. I'm going to list it out term by term here. It was x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Dot, dot. Okay. And so what's the antiderivative? Well, let's throw in our constant of integration at the beginning. There's a constant of integration. And then we term by term integrate, right? What's the antiderivative of x squared? X cubed over 3. What's the antiderivative of x to the 6th? Okay, so 1 over 3 factorial. Antiderivative of x to the 6th is 1/7 x to the 7th, or x to the 7th over 7 factorial, or over 7 times, 3 factorial, 7 times 3 factorial. So it's not 7 factorial, it's just x to the 7th over 7. And then what's the antiderivative of x to the 10th? It's going to be x to the 11th, 11 times 5 factorial. And then x to the 15th? 15 times 7 factorial. Right? Can we write this in closed form? Yeah. We basically go back up here and we find the antiderivative of this thing, right? So this is all constant with respect to x. What's the antiderivative of x to the 4n plus 2? Add 1, 4n plus 3, x to the 4n plus 3 divided by what? 4n plus 3, right? Just power rule. So it's going to be we've got this negative 1 to the n. It's going to be x to the 4n plus 3, add 1 to 4n plus 2, divided by 4n plus 3, and we still have this 2n plus 1 factorial. And if n is 0, you can plug it in and you'll see negative 1 to the 0 power is 0. I get x to what? 0 plus 3 I get x cubed up top, and down below what do I get? 0 plus 3 is 3, 1 factorial is 1, I get x cubed over 3. When n is 1, I get what? Negative 1, I get negative. X to what? 4 plus 3 is x to the 7th. 4 plus 3 is 7 over 3 factorial. N is 2, I get this one. N is 3, I get this one, and so on. Right? So there it is. There is the answer. There is the antiderivative of sine of x squared, which we could not do until we talked about power series. Right? Just in closing then, this is helpful if I do want to evaluate the definite integral, say from, I don't know, from 0 to 2 of sine of x squared. I can use this power series to evaluate it. Now you might say, well, that's an infinite number of terms. But keep in mind, as long as we're close to 0, then the first few terms, maybe these 4 terms here, do a pretty good job of approximating sine of x squared. So I can maybe get a pretty good value for the integral from, I don't know, 0 to 0.1, just, real close. Definitely should get a pretty good approximation by using this as my antiderivative and just evaluating it at 0.1 and getting the answer to the definite integral using the fundamental theorem of calculus. And so, and for a long time, power series were used in computation to help evaluate. How do you find the value of sine of x? Let's just go back to here. How do you find the value of sine of x with a calculator? Right? You just press the button. Well, what's going on? Well, one thing it could be doing, most calculators actually don't do this now, but what it could be doing is use a truncated version of this power series to approximate it. Right? So if you want to find sine of 0.1, what's sine of 0.1? Well, you plug in 0.1 for x here, and you get a pretty good approximation. Okay. So again, power series will help complete our process of finding the antiderivative of all our elementary functions. And that is the end of Taylor series and basically the end of Calculus 2. So we will say goodbye until Calc 3.